will talk about central limit theorems for Poisson functional, and we're using the Malliavin-Stein approach, and I will explain all these things in due time. I will explain what I mean by this. What I want to start with is a bit of a motivation, where we're coming from, why we're doing what we're doing, or what the typical thing is that we study. And so I'm going to start with an example that I will keep using throughout the talk to illustrate what's going on. And so this is one of the things that we study. So you start with a bunch of random points in RD across 0, 1. So you have a space-time coordinates for points. And these are given by a Poisson measure, more on that in a second. And for these points, well, we have these points, and we fix an observation window, which can be some convex set H. And inside this window, we're going to construct a graph. And so this graph is a nearest neighbor type graph, meaning that every point connects to its nearest neighbor, but it only considers neighbors that have a smaller arrival time. So each of these points carries an arrival time, and so we only connect downwards in time, which means that if this is the first point to arrive, nothing happens, but if this is the second point, it's going to connect to the first. If this is the third point, it's going to connect to whichever one is closer, and so forth. So you get this tree growing in time. And what we now want to know is, okay, we have this graph, but now we can make our observation window grow larger and take into consideration the points around here, which means the graph might change as you do that. But we're going to make this grow with the parameter t. And what we're actually interested in is that if we take a function of this graph, so essentially a function of the collection of random points, how does this behave when t goes to infinity? And in particular, what we're going to study in this example is the total edge length of this graph. And not just total edge length, but also you take the length to the edges to the power alpha, which allows you to give more weight to longer edges if you make alpha large. Because alpha is quite large and you have these quite long edges here. You're giving a lot of power to them, whereas if alpha is close to 0, you sort of evenly weight most of the edges. Right, okay, so this is what we're studying, and in particular we want to know, does this quantity satisfy the central limit theorem? And I'm going to give you the answer towards the end of the talk, but for now let's talk about the Poisson measure, which I'm going to introduce in a bit more detail because it's the fundamental underlying object of everything that's going to happen in this talk. So in my example, I took a Poisson measure on RD cross 0, 1, but you can define this on any space X with a sigma finite measure lambda. And essentially, it's a random point measure, but in our context, we always identify it with a random collection of points inside our space X. And then it has some very nice properties, being that inside some subset, the number of points inside the set is a Poisson, is Poisson distributed with parameter measure of the set. So large measure, many points, small measure, few points, and on average, the number of points you get in each set is the volume of the set, so it makes sense. And you have spatial independence as well, which is something that will actually come in later. Because this translates, so the spatial independence is something that's quite important, in that if you have disjoint subsets, what happens in these subsets is completely independent. Right, okay, so this is going to be the fundamental object of everything we're going to deal with, and the Poisson functional is now just a function of a Poisson random measure. Now, the way we're going to study these Poisson functionals is via the Malliavin-Stein method. And so this is a combination of Stein's method, which was developed by Charles Stein in 1972, and Malliavin calculus, which dates from 78. But in fact, the two were only combined in 2009 by Noda and Picati on the Venus space in a Gaussian context, and then shortly after it was done for this Poisson setting that we're in as well. And the first application to stochastic geometry was in 2013 by Matthias Reisner and Matthias Schuld. And in fact, so this combination of the two methods has been quite prolific. So if you're interested, there is a whole collection of papers online. But I'm banding around with a lot of names here, so I want to tell you what this Malliavin-Stein method is and how it works. So here we go. For Stein's method, what we start with is, so we want to show a central limit theorem, so we're going to do this by studying the distance between our Poisson functional and the Gaussian distribution. The distances we're using are these types of distances, so we integrate our two random variables that we want to compare against a number of test functions, which are chosen in some appropriate set. So this can be total variation distance, Wasserstein distance, Kolmogorov distance, any of these. But now, the idea that Stein had is the following. So, if you have a Gaussian random variable, then the expectation of f prime of g minus gf of g is 0 for all smooth f that decays sufficiently at infinity. So for a very large collection of functions, this is true. And in fact, it's not that hard to see, because if g is Gaussian, then you can rewrite this as the integral against the Gaussian density, and then it's really just integration by parts to see that this is actually 0. And the other way around, if this is true for a large collection of functions, you plug in some nice functions that give you some information about the characteristic function of g, and so you can deduce that g is Gaussian. So the fact that g is Gaussian can be determined by some characteristic expression. And so the idea that Stein had was, we're going to introduce a differential equation. And so what we're going to do is we're going to put this characteristic expression on the left-hand side, and we're going to put the difference from the distance on the right-hand side, where we've plugged in the Gaussian already. So instead of f, we have x here, but we're keeping the Gaussian. And then we solve this for f. So f is our unknown, h is given, and this gives us a solution fh. And usually these solutions have very nice properties as well. And now what we can do is, well, we can go back to the distance, and we can rewrite this difference in terms of the solution to the differential equation. And now we've gotten rid of n here, and the fact that we're approximating a Gaussian is encoded in the choice of differential equation here. So you've gotten rid of this clunky term here, and instead you now have something that is much nicer to deal with, especially since the functions fh are usually somewhat explicit and have very nice properties, as in they're bounded, they're Lipschitz, they have bounded derivatives, that sort of thing, depending on your collection of functions h. So this is what Stein's method gives us, and now we have to use Malliavin calculus to bound this thing for Poisson functionals. And the distances that we're considering in this talk are the Wasserstein distance and the Kolmogorov distance. So Wasserstein, we plug in the collection of Lipschitz functions here with Lipschitz coefficient 1. And Kolmogorov distance, we plug in the indicators, which means that we basically take supremum over the cumulative distribution functions. The Wasserstein distance is usually much nicer to deal with in this context than the Kolmogorov distance, because the fact that you use Lipschitz functions gives you much more regularity than you get from the indicator functions. So usually Wasserstein is much easier to do. Okay, so we get this far in our approximation of, in our journey to approximate f by a Gaussian. Now we need to talk about the Malliavin calculus part. And Malliavin calculus is a calculus for random objects, which has been developed in various fields. So you can do this for Gaussians, you can do this in a Poisson context as here. You can do this, I think, for collections of independent random variables, but you can't do it for everything. So it depends on what context you work on. And in a Poisson context, well, the fundamental object of Malliavin calculus is you need a derivative. And so in a Poisson context, this derivative is very nice and easy to state, in that it's just a discrete difference. Because the Malliavin derivative, which we also call the add one cost in this case, is literally just the cost of adding the point x to your collection of functions. So this is the derived mass in x, you add it to your Poisson measure, to your point measure. And so what you do is you evaluate f on your collection of functions where you've added x, and you subtract f on your collection of functions. So it's really just a discrete difference. To illustrate this, let's go back to our example. So we have the original online nearest neighbor graph, as we have here. And then we consider the same graph, but now we have added a point to the collection, which also has some arrival time. And so the graph that we construct in this window is going to look a little bit different. And in fact, we've gained the red edges here, and we've lost the blue edges. So the blue edges are the ones that were present here, but are not present here anymore. And so our difference here is just, if we take again the sum of the edge lengths, it's the sum of the length that we gained minus the stuff that we lost. And so it's something very simple. Now, we can iterate this and take the second derivative, which would be the change induced by x when there is a point y minus the change induced by x when there is no point y. So again, let's look at this on an example. You have twice the same graph, but here we have added the point y with some time coordinate, and so this corner of the graph looks a bit different to what it looks here. Okay, now in both of these, we're going to add the red point x and see what happens. So in both of these, we're going to gain some edges and lose some edges. But if you look closely, you're going to see that the change induced by x in both cases is exactly the same. And that is actually not a coincidence, because that's because the change induced by x is sort of limited in this region up here. So x doesn't care what happens down here in this corner of the graph. So the presence of y has no influence on the change induced by x. And so the second derivative is just going to be 0. And this is a phenomenon that you see a lot in these types of graphs or things that we work with, in that if x and y are far apart, then the second derivative will be 0, because the influences of these points are sort of decoupled or independent or far enough apart from each other not to influence each other. And so this is what I just said. This is a different example. So if you have x, which has some influence up in the corner, what y does down there doesn't matter. And so in some sense, this explains why we might expect a central limit theorem. Because in some very rough sense, you can say that f is the integral of its derivative, which the way I wrote it here is definitely not true, but you can make it precise. And so if these terms here only have local interactions with their surroundings, then that means that in some sense you have a sum of weakly dependent random variables which make up your function. And so in some sense you might expect that there is a central limit theorem. But you have to make this precise. But this is sort of the heuristics of what's going on. And this ties into something called stabilization theory, which makes this more rigorous in that it considers functions that really just look into some specific area what's going on. And it's called stabilizing because, in fact, if you look at this influence here, well, it's cut off by the boundary of the observation window. But if you let your parameter t grow and you make your observation window larger, eventually the change induced by x is not going to depend on anything that happens around the border. So if you make your observation window larger and larger, essentially this portion of the graph is completely self-contained and doesn't care what goes on around it. And so it's going to stabilize as you go to infinity. Right, okay. So with this, let me introduce some results. And yeah, time should be all right. So we now have to make this heuristic precise, and we use the Malliavin-Stein method for this. So this is a result by Laspicati and Schote from 2016, which has a very general setup. So we start with a very general Poisson measure on some sigma finite space X with a measure lambda. We take some functional of this Poisson measure. We say sigma is the square root of the variance and f hat is the centered and rescaled version. That's a notation I will keep using. And then with this, we can find a bound on the distance. So if I put in the Wasserstein distance here, but you can do the same in Kolmogorov. You just get a few more terms. But the distance between your centered and rescaled function and a Gaussian can be bounded by expressions like this. And the only way that f intervenes in these expressions is through the variance, the first outbound cost, and the second outbound cost. So in the end, if you can control the variance of your function, and you can control what happens when you add 1 point to your set of points or 2 points to your set of points, you can derive a central limit theorem. In the end, what happens is that for the most part, this expression here is going to be 0 or close to 0 because x and y are far apart. So this is only non-zero if these points are actually close to each other. And this is usually sort of bounded by a constant because change is regional or local. And so if this is the entire space, this is just going to be something local that doesn't depend on the size of the space. Right, what I also want to draw your attention to is that we have fourth moments of these outbound costs. And while that is nice and well, the fourth moment is sometimes too large for what we have in mind. And for that, we can go back to our example from the beginning. So here I'm comparing an online nearest neighbor graph to a nearest neighbor graph, where we do the same thing of connecting to the nearest neighbor, but we forget about time. So we just pick whatever point is closest, irrespective of time. And as you can see, you get much smaller edges, because this graph is actually the one that's really nicely behaved in that everything is really local, everything is really contained in its own little area. But here, because of the time, you can get some very long edges. So while this graph is in some sense still has a local construction, it also violates this when time is small. So at small time, we get problems here because of the long edges. Because essentially, if this is the first point and this is the second, they're always going to connect no matter how far apart they are. And so we need to deal with this. And it translates into the add-on cost as well. So if you add a point to this graph here, change is going to be small and local. But if you add something that has a small arrival time, your graph will look very different. And so a fourth moment is too large to what we want to do here, because in the end, if you have a power 4, it gives too much power to long edges. And so essentially the long edges take over and your bound blows up. Because you need to keep this small if the edges are long. And so this is one of the results from my thesis, which has the same setup as the one we had before. So we have a very general Poisson measure and a function of that, and so forth. We compare it with a Gaussian, but now we introduce a parameter p between 1 and 2. And then we have a very similar bound, but instead of fourth moments, we have 2p moments here. And because p is between 1 and 2, this can take any value between 2 and 4. So now we can adapt the moment to something smaller as we need it. And I don't know if I will have time to talk about some ideas of the proof in the end, but the proof of this is a bit different to the proof of what we had before, because the fact that you have this Malliavin calculus structure gives you an L2 Hilbert space that you can work with. But the problem is, if you use this L2 Hilbert space structure, you have squares, and squares gives you fourth moments. And that's what you want to avoid. So you have to abandon the Hilbert space structure. So in fact, if I have time, I will show you in the end that this comes from some new functional inequalities in Poisson space, which are necessary to prove this type of bound. Right. There is a similar bound for the Kolmogorov distance as well as before, just it's much more involved. The proof is about twice as long, and there are about twice as many terms to deal with, but it's fairly similar. Okay, so going back to our online nearest neighbor graph result, here is a recall of what we're looking at. So we're looking at the sum of edge length to the power alpha. And it actually turns out that this power alpha has quite some influence because of the long edges of the graph. So it's been shown that if you make alpha too large, then you actually don't have a central limit theorem anymore, because the behavior of the long edges takes over instead of the sum. You just look at some of the longest edges. So it depends on the dimension d of your surrounding space as well. So it's been shown that if alpha is larger than d, there is a limit, but it's not Gaussian. Between d half and d, we don't know. It's conjectured to be non-Gaussian, but we don't know. And then so between 0 and d over 4, there was a central limit theorem shown in 2005. And between d over 4 and d over 2, it was conjectured in 2009, and it's been open since. D over 2 was also conjectured to be a critical point, which it is, as we will see in a second. So with this previous theorem, we can now give a central limit theorem for this entire range here. And in fact, what happens is that the closer alpha moves to this critical point, the more you have to lower your moment condition. So this P is exactly the one that we had in the previous theorem for the moment condition. And we have to adapt it, we have to make it smaller the closer we get to this. But in the end, we get a bound on the speed of convergence to a Gaussian of our rescaled function. And this speed, again, will depend on the moment condition. There's some upper and lower bounds for the variance as well. And for the critical point, we also get some speed of convergence, but for the critical point, the theorem that I showed you actually doesn't suffice. You have to get something that's a tiny bit more refined, in that you can't take moments of your add-one cost. You need to take moments of the conditional expectation of your add-one cost, conditioning on what happens previously in time, and then you can derive this bound here as well. And it really is a critical point, because the behavior starts changing in that the variance gains an additional logarithmic factor, and so it seems sensible that there is no central limit theorem afterwards. But again, we don't know. And it turns out that I do have some time. So let me spend a few moments on how to prove this, or how to approach this. So one of the things that you need to use in the proof is a Poisson inequality, which is sort of a way to introduce this add-one cost into the expression that we had in the beginning, starting from Stein's method. And so in the proof of the original result, they use the classical Poisson inequality, which is in some sense maybe similar to the ones you use in geometry in a philosophical sense, because the variance of any Poisson functional is bounded by the second moment of its add-one cost. Okay. Problem is, if you plug this in, you're going to end up with fourth moment again. So you want to avoid this square here. You need to reduce this to something that is less than a square. And so what we had to show then was that a similar inequality holds for, that should be 1 and 2, not 0 and 1, sorry. So for P between 1 and 2, a similar inequality would hold, in that the P moment of your functional can be bounded by the P moment of your add-one cost. And in fact, you can show this via, so that you have different ways of showing this. You can show this via some Einstein-Uhlenbeck semigroup approach, but you can also derive it from a more general inequality, which is this one, which is the one we also need in order to approach the Kolmogorov distance. So as I said in the beginning, the Wasserstein distance is much easier to deal with than the Kolmogorov distance, because for Wasserstein distance, this inequality here suffices. But for the Kolmogorov distance, you need something that is more involved. And so instead of this, we need to have something that's a bit more refined, which deals with so-called Skorohod integrals. So these are a certain type of integrals in Poisson space, but the point is that you can write every function as one of these things. So if you prove this, you can derive something about the functions, and we get a bound that, again, gives us, that introduces these outbound cost operators. And so we can introduce Malliavin calculus into our proof. And in the end, we can deduce something that really only just depends on these things and on the variance through rescaling. And yeah, I guess this is where we'll stop. Thank you very much for listening.